Hi again everyone. In this presentation I'm going to show you how to calculate derivatives of exponential functions. So we're going to compute a derivative through a limit, and then I'm going to show you how to inform our understanding through the use of technology. So just to refresh your memory, an exponential function is of this type, where a is some positive number known as the base. Oh, sorry, before I get to that, let me share my screen with you. There. Okay, so just to refresh your memory, this kind of function here is known as an exponential function. A is a positive number known as the base, and x is the variable known as the exponent. So you might have something like 2 to the x, or 3 to the x, or a half to the x, or 1 to the x. Okay, they're all exponential type functions. Now, in the calculus of exponentials, a very important question is, what is the derivative of f with respect to x? Okay, so just before we talk about this, let me show you a little graph here. These dotted lines are all exponential curves, and you can see this red line is a tangent to one of those curves at the point 0, 1. Okay, what is the derivative of an exponential function? Okay, so if we use the limit definition of a derivative, then essentially what we want to do is compute the limit of this difference quotient, okay, for this particular f. So that's what we're going to do. All right, so if I replace x with x plus h and f of x with a to the x, then I get this. I can factor out an a to the x, like that. And that can actually come out the front because our limit has nothing to do with x. It just is taking the limit as h approaches 0. So that can come out the front. And I'm left with this. Now, what is this? Well, this is a special limit, and in fact, it is just the derivative of this exponential function at a special point, the point 0. So this is basically f of h. 1 is f of 0. So this then is the, I guess, an alternate a limit definition or limit form of the derivative. So this is just the derivative of f at the point x equals 0. Okay, so even if you didn't understand all of that, that's okay. The really important thing that I want to get across here is that the derivative of f depends on two things. It depends on the product of these two things. It depends on the function itself and the derivative at x equals 0. Now, what is the derivative at x equals 0? It is the slope of the tangent line to the curve associated with the exponential at x equals 0. Okay, so we already know what this is. To compute the derivative at any point x, all we need to know is the slope of the tangent line to the curve at x equals 0. That simplifies things greatly. Okay, so for example, if f of x equals 2 to the x, then the derivative, I'm just going to use the ddx notation for this, is the original function times the derivative at x equals 0, or the slope of the tangent line to the curve associated with 2 to the x at x equals 0. Now, you might think, well, how do I compute this? Well, it turns out that this is just going to be the logarithm of a. Okay, but what I wanted to do was just use a little bit of technology to give you a feel for this and a geometric interpretation. So let me share my my screen with you again. So here I'm using a package called GeoGebra, which is a free package, and yeah, it's got a nice plotting and some CAS capabilities. And in this picture, what I've done is I have drawn in or plotted the exponential function 2 to the x, that's the purple curve. Then I've put a point on that curve at 0, 1, which is a. Then I've put a floating or sliding point, b, on that curve at the point, say, h, comma, 2 to the h, where h is this parameter up here. Okay, so we can now see that the line, the blue line through the points A and B is like a secant. Now, if I make B approach A through the purple line, in other words, I'm letting H go to 0, what we're interested in is the slope of this tangent line as H goes to 0. Now, the y equals constant x plus 1, that is the equation associated with that the tangent or the secant curve. And look what happens to the coefficient of x as h decreases and gets close to 0. The coefficient of x starts at, say, 0.83, 0.82, 0.8, 0.79. It just continues to decrease, 0.77. Okay, it's slowly decreasing. H is getting small now, 0.72, 0.71, down to about 0.69. Okay, so the slope of that tangent curve is approximately 0.69. Okay, so this geometric animation is trying to inform or build our understanding. Okay, all right, so let me go back to here for a second. In this case, the derivative of 2 to the x is approximately 0.69. Okay, that's approximately log of 2. Okay, and if you were to do this for every value of a, you'd be able to define a function log a. Okay, so the derivative of the tangent, the slope or the gradient of the tangent line for arbitrary a is log a. So what it means is the derivative of a to the x is log a times a to the x. Okay, what I've tried to do here is to sort of give you some insight without mentioning logarithms too much. Okay, so that's a little bit on the calculus of exponential functions. Let me know what you think. Your feedback is really important and it's really valued. So if you like the animations, I can do more of them. So let me know what you think in the comment section below. Thanks for watching.